Hi, I'm Swarupa Sel, course instructor for fluid mechanics. In this presentation, we will go through momentum principle and how to find force exerted by flowing fluid on a pipe bend. To begin with, we will study law of conservation of momentum. It states that a body in motion cannot gain or lose momentum unless some external force is applied. So, as per Newton's second law of motion, rate of change of momentum of a body is equal to the resultant force acting on the body and takes place in the direction of the force. So, force is equal to rate of change of momentum. Momentum equation is based on the law of conservation of momentum. So, according to law of conservation of momentum, net force acting on a fluid mass will be equivalent to the change in momentum of flow per unit time in that direction. Force acting on a fluid mass m will be given by Newton's second law of motion, that is F is equal to m into A, where A is the acceleration of the fluid flow acting in the same direction as the force F. Acceleration is nothing but the rate of change of velocity. So, A is equal to rate of change of velocity, that is dv divided by dt. So, F can be written as F is equal to mass into acceleration. Acceleration is dv by dt. So, we get d of mv divided by dt. The equation which we already have seen is termed as the law of conservation of momentum, and the same equation can be written as F into dt, which is equal to d of mv, and this equation is called as impulse momentum equation. So, impulse of a force F acting on a fluid of mass m in a short duration of time dt is equal to the change of momentum in the direction of force. Consider steady non-uniform flow in a stream tube. Let A1, V1 and P1 be the area, velocity and pressure at section 1. Similarly, A2, V2 and P2 be the area, velocity and pressure at section 2. In time delta t, volume of fluid moves from inlet to a distance of V into delta t. So, volume entering the stream tube is area into distance. Area is A1 at section 1 and distance is V1 into delta t. Mass entering stream tube in time delta t is equal to density into volume. Density is ρ1 into volume is A1 V1 delta t. Momentum of fluid entering the stream tube is nothing but mass into velocity. So, mass is ρ1 A1 V1 delta t into velocity is V1. Similarly, momentum of fluid leaving the stream tube is equal to mass into velocity. So, it is ρ2 A2 V2 delta t into V2. To find force on the fluid, use Newton's second law of motion, that is force is equal to rate of change of momentum. So, F is equal to rate of change of momentum is momentum at section 2 minus momentum at section 1 divided by delta t. Momentum at section 2 is ρ2 A2 V2 delta t into V2 minus momentum at section 1 is ρ1 A1 V1 delta t into V1. From continuity equation, we know that Q will be equal to A1 V1, which is equal to A2 V2. So, for fluid of constant density, we will have F equal to Q rho into V2 minus V1, which is equal to m into V2 minus V1, where m is equal to rho A V. AV is nothing but Q. So M is equal to rho into Q. Now we will find out how to get the value of force exerted by flowing fluid on a pipe bend. So here we can see a pipe of varying diameter. So the area at section 1 is A1 and area at section 2 is A2. Here the diameter of the pipe is decreasing. Let pressure at pipe of section 1 be P1 and pressure at section 2 will be P2. So if we consider this as x and y direction, the force along x direction will be Fx and force along y direction will be Fy. We need to find out Fx and Fy to find the force exerted by the liquid on the pipe bend, because F is equal to square root of Fx square plus Fy square. Let velocity of fluid at section 1 be V1 and V2 is the velocity of section 2. That means it is the velocity of fluid at section 2. Since V2 is inclined, we need to find out its horizontal and vertical component. The pipe is bent at an angle of theta. So, horizontal component of V2 will be V2 cos theta and vertical component of V2 will be V2 sin theta. Similarly, P2A2 is acting on section 2 and it is inclined at an angle theta. So, its horizontal component will be P2A2 cos theta and vertical component will be P2A2 sin theta. Here we need to give attention to the values of V2 and P2A2 along x and y directions. So, let us consider fluid flowing through a pipe which is bent as shown in figure, and two sections are considered. So, V1, P1, A1 are the velocity, pressure and area of section 1. Similarly, V2, P2, A2 are velocity, pressure and area of section 2. Fx is the force exerted by the flowing fluid on pipe bend in x direction and Fy is the force exerted by flowing fluid on pipe bend in y direction. So, the Fx and Fy are the forces which are exerted by the flowing fluid on the pipe bend in x and y direction, which will have to be found out to get the value of F. Considering Newton's third law of motion, force exerted by the pipe bend on the flowing fluid will be Fx and Fy in x and y direction. There will be some other forces also acting on the flowing fluid, that is P1A1 and P2A2, which are the pressure forces acting on the flowing fluid at section 1 and 2. Let us use the momentum equation and we will have the equation for x direction, that is the net force acting on fluid in x direction, which is equal to rate of change of momentum in x direction. So, it is P1A1 minus P2A2 cos theta minus Fx, which is equal to mass per unit time into change of velocity. So, P1A1 minus P2A2 cos theta minus Fx is equal to rho q v. V is nothing but change in velocity, that is final velocity in x direction minus initial velocity in x direction. So, we get the equation as P1A1 minus P2A2 cos theta minus Fx is equal to rho q into V2 cos theta minus V1. So, finally, we get equation for Fx as rho q into V1 minus V2 cos theta plus P1A1 minus P2A2 cos theta. Similarly, we will use momentum equation to get the equation for y direction. Net force acting on fluid in y direction equal to rate of change of momentum in y direction. So, minus P2A2 sin theta minus Fy equal to mass per unit time into change of velocity. Minus P2A2 sin theta minus Fy equal to rho qv. So, it is rho q into final velocity in y direction minus initial velocity in y direction. Final velocity in y direction is v2 sin theta and initial velocity in y direction is 0 because velocity at section 1 is only along x direction. So, its component along y direction is 0. So, once we rewrite this equation, we get Fy equal to rho q into minus v2 sin theta minus p2a2 sin theta. Once we get the value of Fx and Fy, we will be able to find out the resultant force, which is equal to square root of Fx square plus Fy square. And the angle at which it will act can be found out using formula theta equal to tan inverse of Fy divided by Fx. Thank you.